In the previous class, I have discussed about the chromatography techniques. Chromatography, what is chromatography? It is an analytical technique which is widely used for separation, isolation, and identification of the related chemical compounds. Which can be, this technique is used for mainly for separation of compounds or organic molecules are synthesized. So, and previously I have discussed about paper chromatography, thin layer chromatography, and gas chromatography, how it works, and retention factor, how you are going to calculate the retention factor of the chromatography. So, and what are the sub instrumentation of gas chromatography? Like what pressure control for gas chromatography use different mobile phases such as inert gases like helium, hydrogen, nitrogen, carbon dioxide, and argon are used as a mobile phase in the gas chromatography. By using the different inert mobile gases, we are going to analyze the sample separation. So samples are heated and are converted into gaseous form in the thermostat and pass it to the column to the detectors to identify the different molecule present in the given sample. So that is the principle in the gas chromatography. Today we are going to discuss about HPLC, that is known for high performance liquid chromatography. So in HPLC is nothing but, this is also a liquid chromatography where a new technique was named here as high pressure or high performance for liquid chromatography. HPLC means high performance liquid chromatography. So HPLC is mainly of liquid chromatography. It is a type of liquid-liquid chromatography. Means even the mobile phase is liquid and the stationary phase also is in liquid form. Stationary phase is nothing but the sample what we have taken, which is in the liquid form. So that is known as liquid-liquid chromatography. The column size of this HPLC will be around, means HPLC for liquid chromatography, it's the high performance liquid chromatography. The column size will be around 2 to 5 millimeter diameter and length approximately, which will be around 50 centimeters in the packing. So here it is mainly used for the separation of analysis of variety of solutes. Solutes are nothing but the stationary phase. Solutes are the samples for a complex mixtures of small amount. So it is having some various modes here. In the HPLC, we are going to study different modes such as absorption chromatography, partition chromatography, and reverse phase exchange chromatography, ion exchange chromatography, and ion chromatography. So these are described with respect to stationary phase packing material. You should be knowing this point very much. Here we are going different chromatographies we are there, such as ion exchange chromatography, absorption chromatography, partition chromatography, reverse phase chromatography. These are all with respect to stationary phase. Only the stationary phase of this instrumentation will be varied. So it is named with different chromatographic techniques here. The mobile phase will be different, means solvents are used. For different chromatographies, we are going to use different stationary phase. For example, in the previous liquid chromatography, I have used silica or aluminium as a stationary phase. Here we are going to analyze, means use of stationary phase depends on the different chromatography. It also depends on the samples what we have taken. So that is the basic principle here. For different chromatographies, we are going to use different stationary phase. Some typical applications are used for HPLC, such as in the drug abuse. We can see the different molecule present in that, and the chiral separation. By different chromatographic techniques, we are going to make use of different separations, chiral separation, separations of amino acids like nucleic acids, and also cation, anion separations, isomers can be separated using different chromatographic techniques. So this is the basic what we are going to study in this unit. So before getting into the topic, we should be knowing what are the objectives of this unit. So here we are going to what is liquid chromatography and principles and instrumentation. We are going to study advantages and applications of high performance liquid chromatography, types of columns and detectors we are going to use for different chromatography techniques, and principle and application of size exclusive chromatography, gel permutation, ion retardation, normal phase and reverse phase chromatographic techniques. So this is the instrument what we are going to see in the pharmaceutical companies are analyzing the HPLC. So this is the working block diagram of the HPLC liquid chromatography here. Here we are taking solvent. This one acts as a mobile phase and pumped with a different pressure, and we are going to inject the sample here, ample, and passes through the column. This is the basic principle how the HPLC works, and passes through the column, and it is elevated with a different concentration. The bands are formed. You can see in this one. When the solvent sample passes through the column, different bands are formed for different molecule. So it is separated. We can separate those by LUT in the different concentration. So these are detected by detectors, and the signals will provide different signals will provide different. This is the chromatogram. By detectors what the signals have passed, you can form the different chromatogram, and different peaks provide different compound present in the given sample. Next is this is the introduction what I have said, and the basic principle in the HPLC is it is for the separation of high performance liquid chromatography. It is similar to the liquid or column chromatography. Here we are going to use high pressure for the separation of the liquid samples. Before what I told in the HPLC, we are going to use sample in the liquid form. It can be dissolved in the solvents which are using in the mobile phase also, or with different solvents we have dissolved and uh, injected to the column through liquid. So here it differs with regard to the size of the column and sample also. Here this one is used for the first one, which is shown here. This is the column chromatography what we are taken previously discussed. This size will be around 4 to 5 centimeter diameter, which is more than the what we have used in the what we have taken in the burette. Size of the column will be more burette more than 4 to 5 centimeter. It will be more compared to the burette. And next is this is the HPLC used in HPLC column, which is having the size of 1 to 3 millimeter. See here, column diameter, which is having 10 to 15 millimeter for column chromatography, and this is for these two are for HPLC, where these two are for HPLC used, which is the column diameter will be around 1 to 3 millimeter, and here for 2 to 6 millimeter, and the pressure will be around 30 to 50 atmosphere and 100 to 200 atmosphere pressure. So why there is a difference? You can note it here itself. This is the normal chromatographic technique, and these two are high performance liquid chromatographic technique. So the pressure will be more compared to, if you see, this is in the liquid chromatography technique, it is around 1 atmosphere. In HPLC, it will be around 30 to 50 atmospheric pressure. And well, coming to the another small chromato column, where it will be having 100 to 200 atmospheric pressure, so that HPLC with microparticles packing are used for this in the column C, and in the HPLC with particular packing, which is in the column B. This is the difference between the normal chromatography and the HPLC chromatographic technique. And in order to achieve this desired separation by HPLC, we are going to operate certain conditions, including retention time, wear, and pressure, what I told, 30 to 50 atmospheric pressure, which varies for HPLC, and number of plates needed to be optimized, different bands which are need to be optimized, means it should be separated while eluting. So and this is the chromatogram for this is the chromatogram for logarithm plot for reduced peak height, means the column peak height of the is reduced against the reduced velocity. If the peak height of the column is reduced, even the weak velocity also reduced here. So it all even the retention factor also will be increased. So as the here we are taken three different what materials for such as A and B. This one is denoted in the green, and this is for the C molecule. And reduced plate height. If A is the sample which is having the porous particle size of the, these are all A, B, and C are the size of the stationary phase. So stationary phase which is having different size. If the B is having around 1.2 solid here, which shows inclination with respect to velocity. This x-axis denoted as the reduced velocity, when the velocity is reduced after the injection of the sample to the mobile to the stationary phase. So this is log h is nothing but the height of the column. So when you are using different porous size here, for A is 0, so it is giving a well packed column, and it is A is, if A is 0 means it is a well packed column, and B is nothing but it is having 1.2 porous size. So it will be having some rate of velocity of the sample will be reduced and increased with the increasing of the column height. So with respect to this one is C, and with respect to B is having the solid size of particle of 1.2, where and it is completely porous. So the small molecules, here the small molecules with respect to it has been reduced for particular particles, and the porous particle decreases to 0.3. And next is instrumentation. Some general instrumentation for the HPLC is one or more solvent reservoirs are used, and the mobile phase pump is used for the sampling of the system. Here we can see detailedly. Yes. Here one or two solvents which are taken. These are the solvents. One or two or three solvents can be used for different polarity. Polar and non-polar solvents can be used for the separation of the sample. And further, a pump is delivered to give high pressure, used for the high pressure, and a guard column where a linear filter to be used to prevent the contamination. Here, sorry. Before the column, a small guard column is used to remove the contamination of the solvents or the samples, which is it can be removed using the guard column. And further, separation column chromatography containing packing to accomplish desired separation can be from the analytical column can be seen, and a detector cable enough for measuring the solute concentration. Detectors are used to measure the concentration of the solute. So the solute which are present in the column is elevated, and those concentrations are detected by the detectors, and the signals are passed to the control station, which is it will be converted into the chromatogram, and you can see the different peaks for different molecules. So next is sample injection system. In this sample injection system, here the injection of the sample uh, and the mobile phase are injected separately. So this is the technique where you used for the sample injection to the column. This is the part where in the previously what you have seen, this is the sample injection. Yeah, this is the mixing chamber, what they are told. This is the sample injection chamber where it will get mixed with the, but the mobile phase are injected separately and the sample is injected separately. It gets mixed in the mixing chamber. So this is the system where the sample is injected and further it is passes through this, and pass the sample out means it will connect it to the column, and even the mobile phase what we are injected here, the mobile phase is injected and it is passed to the another side where it is connected to the sample mixing chamber. And here we are going to use different columns. Coming to the part of the instrument where we are going to study the column which we are using for different samples. So in HPLC, we are going to use stainless steel column also, polyether ethyl ketone column, divisal column, titanium column, fused silica glass column, or glass liquid SS. So column tubing materials and its uses generally depends on the sample. So what samples has to be separated. So you will be using accordingly. And for 316 stainless steel column, it will be used for good high pressure system, and it may most organic. It can be separated for most organics solvent except methylene chloride, tetrahydrogen ferrite, DMSO, and concentrated sulfuric acid, nitric acid for high pressure up to 800 500 psi. So it is good for metal-free biological system for separation. And next is polyether ketone. This one, oh sorry, this is the peak for this separation. And next is Terzel, where inert column for metal-free applications. So Terzel are used for titanium columns are mainly used for the withstanding the pressure up to 5000 psi, and it is a corrosion resistant. And titanium column are most expensive. And further, fused silica gels used for the capillary liquid chromatography technique. And glass chromatography is mainly used for the limited pressure range. It cannot be pressure cannot be more, increased in the glass chromatography. So glass liquid SS inert withstands pressure up to difficult to know whether the glass is broken or not. So it can be limited to some pressure range. It cannot be used in the high pressure. So column length it may vary for different from 10 to 30 centimeters with inner diameter of 2 to 5 centimeters, providing 40,000 to 60,000 plates per inch. Means plates are different bands which can be separated. So the length of the column which may vary from 1 to 30 centimeters, and diameter it may vary from 5 to 2 to 5 millimeters, the circumference. So the longer the column, the large number of the plates, but also speed of separation will be more. So next, and in that we are going to next is the guard column, and what we are seeing in the instrumentation. Yes, this one. Here, a guard column is a short column. It can also be called as pre-column, and a guard column which serves as a saturated mobile phase with the stationary phase, so that loss of stationary phase in the column are minimized. Some of the stationary phase is nothing but the absorbent which are used in the column. So it should not be eluted by using different solvents. Next is the packing materials. Different packing materials used in the column. We are going to use these are the stationary phase or packing materials, silica and alumina. In silica, there is a different packing material such as corrosil, which is having the 37 to 50 micrometers of porous size, and Vardic, which is having 30 to 40 micrometers. And for pellicular size in the microporous, pellicular is the porous outer shell of an impermeable particles. So in the microporous, what we are Licosob, which is having the microporous range of 510 to 20 micrometer. So micro pack also it can be used, micro pack and porosil, and these are for different samples we are going to use different uh, column packing. So for aluminium you can use perisorba, and in micropack which is having 5 to 10 micrometer, and sulfate which is having, that is also having different, which is made up of aluminium here. And these are the packing materials which are generally used for different samples. It depends on what separation you are going to make, whether you are going to separate whatever for the separation of cation anions and isomers, for nucleic acid separations. We are going to change the only the stationary phase for different techniques such as adsorption chromatography, partition chromatography, for reverse phase chromatography, ion exchange chromatography. We are going to change the packing materials. These are the packing materials for different separations, for such as chiral separation, for amino acid separation, nucleic acid separation, cation separation, anion separation, isomers, and also samples isomer separation can also be done using this separate stationary phase. And next, in further, while using this, these are the stationary phase. You should be knowing. Again, you should not be asking what is porosil, what is micropack. These are the stationary phase used for different separation technique. And these absorption packing retain solute molecules, and almost it exclusively it is having internal surface porous size. And for the and in the porous there are different porous for spherical bonded phase, porous layer beds, and porous particles and macro particles. Uh, Here we are going to discuss types of bonded phase for different samples. So A is the this A is the bonded phase, and B is the topography of the ligands. Ligands are nothing but the molecules, and size of the ligands and its size. For monolayer, it will be having same in the ligand size. It will be in the DIMS, and the size of the ligand is short. So in a cross-linked layer or cross-linked polymers, which are can be used, types of bond. Here it is formed different, and it is diluted in the ligand phase, and further size of the ligands will be very long. So in the multilayer, the bond phase will be in the multilayer bond phase. This one is, and further the ligand size will be in the control space. The size of the ligands will be in the within the limit, and the size of the ligands here. Sorry, this is the topological ligand design, and this is the bulk structure. Size of the ligand is in the bulky size. So the coating of the bonded fates, the coating also, it depends on the coating also. So coating is in the different phase. So the topological ligand here, which is having which in the which is in the bulk. So the size of the ligand also is in large size. And it may be noted that the different packing materials, these are the different packing materials where the packing materials are used in the different types for techniques for absorption, partition, ionization. Different, what I've told earlier, we are going to use different packing materials for different separation techniques such as absorption, partition, ionization, chromatography, and size exclusive chromatography. So coming to the next is the absorption chromatography. In what is absorption chromatography? It is the technique for the separation of chemical mixture based on the interaction of the absorbent with the absorbent. So the substitution of a chemical mixture based on the interaction of the absorbent with the absorbent. Absorbent is nothing but the sample, and absorbent is nothing but the which we used in the stationary phase. So the separation, it is based on the separation, a chemical mixture. So here the main mechanism is the interaction of the OH group with a polar or unsaturated fractional group for the solvent molecules by hydrogen bonding or doper interaction. So we can see the what we can see OH group. So OH group determines the activity of the absorbent and thereby interaction of the solvent. So OH group can be divided into three types: well free and siloxane bond free SiO(Si), and hydrogen bond interaction can be seen for OH. So this is the structure of the silica gel. This pink color, which is sorry, this is the structure of the silica gel, which is having the interaction with the mobile phase. Uh, uh, Mobile phase of the sample. So there will be different interaction to get separated. So acyl free OH interaction and siloxane in bond interaction and hydrogen bond interaction will be there for the absorbent. So the interact with the functional group. These interact with the functional group of the solvent molecules. So in absorption chromatography, it is the less influenced by difference in molecules. For molecular weight, by certain, it can be molecular weight can be determined, and also by using a functional group. For the sample, it is having the functional group of it can be interacted with the hydroxyl group and it can be separated. So molecular weight, but certainly of the fractional group. And further compounds of low moderate polarity, which is in the compounds which is having the low moderate polarity, absorption chromatography makes possible for separation of the complex mixture also. And next is the partition chromatography. In partition chromatography, it is a technique where the separation of the components between two liquid phase via solvent and the film of solvent used in the column. So in the partition chromatography, it is separated of components between two liquid phase. One is the solvent which is used in the mobile phase, and the one more is the film of solvent which is used in the stationary phase in the column. So it can be subdivided into liquid chromatography and bond chromatography technique. Further, in the liquid chromatography, a stationary in the stationary means liquid is the station in LLC. See, for liquid chromatography means both liquids. So mobile phase also will be in the liquid and stationary phase also in the liquid. So a liquid stationary phase is it is retained on the surface of the packing by physical absorption method. So the absorption takes physically. So here with the bond phase, stationary phase is uh, for another type that is known as bond uh, phase chromatography. The stationary phase is bond uh, chemically to the surface of the inert support. So that is the bond phase chromatography, and the most yeah. Here, the most useful bond phase. This is the formation of the bond where, and further, the bond phase coating of siloxanes formed by the reaction of hydrolyzed surface with this is the uh, organochlorosilane. When hydrolyzed gives siloxanes. This is formed. Siloxanes are formed on hydrolyzed. This is the organochlorosilane. And next is yes, the it is the relation between the samples here. What samples we are taking, column packing, and the mobile phase. What we are going to use. This is shown in this tabular column, where we are going to study the relation between the polarity of the sample with the packing of materials and the mobile phase in the reverse phase HPLC. Here sample for low moderate polarity soluble in aliphatic hydrocarbon. The column pack will be bonded with C18 column. So the mobile phase will be methanol and water with a different ratio are used for the eluting of the mixed sample. So, and for moderate polarity, we are going to use the column packing bonded with C8. So, the mobile phase will be acetonitrile versus water. Two solvents are used in the mobile phase. Further, for high polarity, which are soluble in lower alcohols, it can be used. Column packing will be bond C2 bonded columns are used packing, and 1,4-dioxane or water used for the high polarity. So here, when the rotation increases with the hydrophobic character, hydrophobic is nothing but the which is not absorbing water. That is known as the hydrophobic character of the solute sample. So this is the all in the partition chromatography. And next is ion exchange chromatography. In ion exchange chromatography, this is a technique where the molecules separated on the basis of their change of the eluted using solution of varying ionic strength. It depends on the separation on the varying of different ionic strength. So this is known as ion exchange chromatography. And the column packing having charge bearing functional group attached to polymers matrix are seen here, and the functional groups which are permanently bonded ionic groups associated with counter ions for the opposite charge. Uh, for example, if you take here for carboxylic acid and phosphate are used as exchanging of anionic species. These are used where, and further this is the different stationary phase in the separation of samples used. And this ion exchange film is nothing but the stationary phase of intercore, where for pellicular with ion exchange film, that is in the A, and B is the exchanger bits coated with superficially with the porous resins. These are different uh, absorption used in the column of stationary phase for different uh, porous size which is can be separated. So during the preparation of this ion exchange by silyl it is silyl is nothing but the introduction of one or more substitutes to silyl group. It can be denoted. It can be denoted as R3Si. It is denoted as silyl group. So to a molecule. Here we are using styrene. This is the styrene, and further in the preparation of ion exchange chromatography, you are using silyl vinyl group for is choose for the R3. This is the silicon monoxide, and further styrene is used to form the bond to form the polymerization of styrene, and further the bond phase is treated with the the treated further the bond phase is treated with the this one chloromethyl ether. This is the chloromethyl ether, and subsequently with the hydroxy ethyl methylamine dimethylamine. So you can get the two different weak anion exchanger and strong ion exchangers are separated, and this is the hydroxy ethyl dimethyl amine. So we can be separated with weak anion and strong ion exchanger. So here hydrophobic polymers allows the separation of these hydrophobic polymers, the polymers which is having the separation of proteins, nucleic acid and other large ionic molecules can be separated by this ion exchange chromatography. This is the concept. And next is the size exclusion chromatography. This is mainly used, this method is used in which this method is size exclusion chromatographic method is in which the molecules in solutions are separated by the size or molecular weight. It can be separated by size or the molecular weight in the size exclusion chromatography. By using this technique, it can be separated by the size or by molecular weight. So this technique is used for the separation. So styrene, here we are going to use styrene divinyl benzene polymer. Allows the, this is used as an absorbent in the stationary phase. Allows the fractional with a molecular weight range of 100 to 500 million. This is denoted as millions Dalton. This will be denoted as Dalton, where the porous size of different polymers have different uh, eluting rate that can be seen here in the table. Here, the properties of typical commercial packing for size exclusive chromatography for type of polystyrene divinyl benzene and silica. These are different absorbent used in the stationary phase. So the particle size of 10 micrometer, and this is also for 10 micrometer, which is having the porous size up to 10 to the power of 2 to 10 to the power of 5, where silica which is having from 125 to 1000 Armstrong, and the molecular weight, this is not 8, this is the weight, molecular weight from for polystyrene divinyl benzene while you are using, it can be determined up to 700 to 5,000 to 5 lakhs, up to 5 into 10 to the power of 15 to 10 to the power of 10 to the power of 6. So up to those molecular weight it can be separated. While using silica as an absorbent, it can be from 5 into 10 to the power of 4 to the 20 into 10 to the power of 5 size of molecular weight can be separated using silica as an absorbent. Next is ion exchange chromatography. Yes. It is mainly used to separate ions and polar molecule based on their affinity to the ion exchanger. So the main principle is to separate the ions and polar molecule based on their affinity to the ion exchanger here in the ion chromatography. So it is used for the mainly used in the water chemistry analysis and to measure the concentration of major anions such as chloride, nitrates, nitrile, and sulfate. Anions can be used to measure the different concentrations of major anions can be measured here for chloride, nitrates, and nitriles and sulfates, and also major cations also can be measured, such as lithium, sodium, ammonium, potassium, and calcium. Also in magnesium, cations can be measured. Different concentration, the concentration of anion and cation can be measured by using ion chromatography. Here the separation of anion and cation takes place, and this is the instrumental separation. So here we are going to use dilute reservoirs, such as mobile phase, different solvents, polar and non-solar solvents, and it is pumped towards the column, and where the sample is injected. Further separation is taken place in the column, and the different elites are collected in the conductivity cell, and it is recorded. The chromatogram is recorded. Same principle, but we are going to use different mobile phase and stationary phase, and we will get the chromatogram of the concentration in separated molecules. That is the principle behind all the chromatography. So next is the chiral chromatography. Here, chiral chromatography means we are going to separate chiral of the enantiomers, where which is having what, same molecular weight but different structures. So we can isomers, different isomers can be separated using chiral chromatography. So here chiral components of separated systems capable of interacting with enantioselectivity with enantiomers to be separated. And the main use of this chiral chromatography is for separation of optical isomers, where isomers means just having same molecular weight with different structures, so that can be separated using chiral chromatography. The separation of enantiomers by HPLC using chiral stationary phase. So the solvents mobile phase will be same for all the chromatographic techniques, where we are going to use polar and non-polar solvents. In the stationary phase, we are, so the separation of enantiomers by using chiral stationary phase. We are going to use different stationary phase for the separation of isomers. So, for example, if you take here we are taken one amino acid. Material used in the stationary phase for separation, it can be natural protein, cyclodextrin, or polymers of cellulose, amylase, and macrocyclic glucopeptide can be used in the stationary phase in the chiral chromatography. So, for example, here we are taking one amino acid, and proline has been bonded with proline P D-vinyl benzene, that is, and the a cross-linked copolymer has been formed here. This is the amino acid. Sorry, excuse. This is the amino acid where cross-linked copolymer has been formed by copper. So the stationary phase of the separation of this resin mixture as seen by linking using cross-linked copolymers. So your analyte enantiomers are to be separated by this analyte enantiomers will be separated by tertiary complex. So this the indirect method are based on the covalent formation of diastomers by reaction with the chirality deviating reagents such as the separation can be achieved. So by using copolymers, it can be separated. And the illustration for the tertiary complex formed between the L-proline bonded phase and the analytic amino acid. This is the L-proline bond phase, and the analytic amino acid and copper 2 plus ions are formed. And next is your solvent supply system. So, in solvent supply system, natural and composition of mobile phase in the liquid chromatography plays an important role as it provides a dimension in terms of retention time for experimental here. So solvent supply system means how the solvent are supplied to the system. So natural and composition of mobile phase in the liquid chromatography plays an important role in providing the dimension in terms of retention time for the experimental. So in the column, if you see the retention time can be varied by using of different solvents. So the concentration of the solvents also matters here for the elution of the for the eluting of the sample. So the ratio of the polar and non-polar solvents, uh, it may depends. So some of the general criteria for the mobile phase means mobile phase is nothing but the solvent which are being used for eluting of the sample. It should dissolve the sample. It should be having the capability of dissolving the samples which are injected to the column. The mobile phase solvent should be having the capability of dissolving the samples, and it should keep the column stable. The column should not get dissolved in the solvents. Means the absorbent which are used in the column should not elute. Only the sample should be dissolved in the given solvent. So it should be compatible with the detectors where high concentration, some of the uh, high concentration will not be detected. So it should be having some ranges. I will let you know in the detector next step where we are going to study with the different detectors what we are going to use. And here we are going to, these are the general criteria. And further, the viscosity should be not be high, means it should be the viscosity of the given solute should be low. It should not be very high. I means viscosity. I means that is the example for when you are taking water. Water is having low viscosity, and high viscosity means you can take example of syrup. So compared to the syrup, the viscosity of the water is very less. So the even while you are selecting the solvent here, the viscosity should be low, and the active fluoride should be avoided while using glass columns. So it should not break. So we should use the some of the active fluorides while using the glass columns. The eluting power of the solvent is determined by its overall polarity. So while you are using polar and non-polar solvents, the eluting of the sample, it depends on the solvent which one you are using. 1:2. The we can vary the solvents of polar and non-polar concentration so that we can elute the sample easily. So some of the this table is not given. And next, there are given some of the tables in the examples for the solvent and in mobile phases also. And I'm going to discuss about the gradient illusion. Here we are going to use different, that is nothing but the, it involves the continuous change in the composition of the mobile phase. Gradient illusion is nothing but the change in the concentration of the mobile phase. So these are the reservoirs we are with the three different mobile phase. For example, you can take water, ethanol, pet ether, different concentration of polar and non-polar. So the samples get eluted, which is having more affinity towards the given solvent. So here by gradient illusion, the mixture flows to the column. So finally, this mixture is flown to the column with different ratios. So the commercial liquid chromatography are designed to mix two or more solvents, which gives a progressive manner from 0 to 100% of one component. So you can give dilute resulting from 0 to 100% here. This is the gradient illusion. And next, we are missing some of the slides here. Once again, I will some of the slides are missing here in the. Yes, I will discuss this HPLC performance, and further some of the topics which are missing I will open in the SLM and I will continue the topics. And so here, this is for the performance of sub HPLC detectors. Different detectors are used for the depending on the samples. So detector properties, it is having absorbance, fluorescence, electrochemical conductivity, refractive index, mass spectrophotometry, FTIR, light scattering, optical activity, photon ionization. This depends on the sample of the system which we are going to use this detector. So typical LOD is the loss of drying. How much the drying of the sample is done. On that we are going to use different detectors here. The linear range here it is given, and the commercial availability, all are commercially available. So some of the advantages of HPLC. What are the advantages as a senior? It is very fast separation method uh, with analyzing time as small, less than a minute. For some cases it can be separated within a minutes. It is the very fast separation method, and HPLC is useful for separation method with high resolving power and quantitative analysis. Quantitative also it can be analyzed using HPLC. It is especially used for resolving optical activity of the compounds through different types of columns, which is chiral stationary phase are used. Optical activity of the compounds also we studied using this, and the technique for applicable for small amount of samples where one traces of amount of solutes may be determined, and HPLC has major widely applicable for pharmaceutical and food processing industries. These are the advantages. Some more advantages are there. Go through this in the ISLM. You will get which are the easiest points you can note down and try prepare for the exam. There are lots of advantages in the HPLC. And solvent supply system, we are going to use different solvents here. Uh, Pentane, hexane, cyclohexane, carbon disulfide, chlorobutane, diethyl ether, chloroform. These are the different solvents. Depending on the samples, we are going to use different concentration of different samples. So here epsilon naught is the this epsilon naught is the vacuum permittivity. So how much the it is having permittivity. So SiO2 is the silicon dioxide. The vacuum permittivity of the silicon dioxide is the vacuum permittivity of the aluminum oxide. So and their viscosity it is seen here. What I told in the advantage selection of the solvent. So it should having low viscous. So this for these solvents there is also denoted with different viscosity seen here and their refractive index. These are the different solvents and their characteristics in this table. And next is and this is the column diameter for different millimeters and the flow rate of linear velocity means the flow rate of the eluent here 0.02 milliliter per minute the flow rate is. So for the column diameter of the column 0.51 is having the eluent rate of 0.02 milliliter per minute. And further gradient illusion, what I told, it is we are going to use three different solvents: polar, non-polar, and polar different. And next is we need to discuss about the pumps which are used in the chromatography. Here, a variety of pumps are used to maintain the flow rate and pressure of the mobile phase. Why pumps are used to maintain the flow rate and to create the high vacuum pressure. So the pumps are used in the chromatography. Here and it is also used in the degasser needed to remove the dissolved air and gases present in the solvent. So pumps are it will be having the atmospheric pressure of 100 to 400 atmospheric pressure. It can be created in the using pumps. So further there are different types of pumps present and the first one is reciprocating piston pump. In this you can create the atmosphere vary from 34 to 400 microliters. It can be separated using this pump. That's all in this. We are going to use different pumps for the to maintain the flow rate and the pressure of the mobile phase. So we are going to use different pumps here. And the second type is the syringe type displacement pump. In this, the capacity will be around 250 to 500 ml can be pumped to the column. So it is having more compared to the previous one, which is 35 to 400 microliters. And this is syringe type displacement pump. And next is the it can also give high pressure capability of 200 to 475 atmospheric pressure. And next is the constant pressure pump. Here it is generated high liquid pressure which is having 1 to 400 atmospheric pressure. And next is pneumatic pump. In this type, these types of pumps are simple and inexpensive, which is having free pulse free but suffer from limited capacity and pressure output. Just you be knowing the names of the pump, that's enough for this. And coming to the next is the detectors. Yeah, why detectors are used? Detectors are used to why used for selective separation and accumulating the determined compound present. So detectors are used. So here some of the good detector detector must have the following characteristics. These the point where you should be knowing some of the good detectors which is having the characteristics are it should have linear response to solute concentration in the range of 0.1 milligram microgram to milliliter to 1 nanogram to milliliter. It should have linear response. It should respond even the flow rate of 0.1 microgram is can be detected. So such type of detector should be used, and it should respond to solute only, not with the solvents. It should only detect the solutes. Means solutes are nothing but the samples. It should not respond to the solvents. Solvents already will be knowing which solvents we are going to use in the mobile phase. So it should only detect the solutes or the samples which are so, and it should be intensive to change the temperature. It should not sensitive to the temperature. While using in the gas chromatography, it is converted in the thermostat. The columns, the samples are converted into gas phase. So by varying the temperature, also it should not, or it should not vary. It should be insensitive to the change in the temperature, pressure, and the flow rate. So these are the main three uh, characteristics for selection of good detectors. So some of the detectors here you can use bulk property detector, solute property detectors. In the bulk property, these types of detector measure an overall change in the physical property of the mobile phase. Whatever the changes which takes place in the mobile phase, it can be measured without any solute. So, for example, refractive index, dielectric constant, density, electric and thermal conductivity of the vapor pressure can also be measured here. These are the things can be measured. And next is solute property detectors. These respond to physical property of the solute that is not exhibited by the pure mobile phase. The response to the physical property of the solute that is not exhibited in the mobile phase. Only the physical property of the solute can be detected. Here, HPLC detector must meet the following requirements, such as selective response towards the one or more classes of solute. It must have small or compatible with the liquid flow. It should have a good stability and responsibility. These are the for HPLC detectors. So these are the characteristics it should be having. It must have low. It should have good stability and reproducibility. It must have high reliability and ease of use, and it should have linear response rate. It should respond with the small amount of the dilute also. These are the main characteristics of these detectors, and these are some of the detectors properties what we are going to observe. Absorbance, fluorescence. It can observe fluorescence also, observation ratio, electrochemical detectors, conductivity can be detected, refractive index, and infrared can be detected, mass spectro, mass means molecular mass also it can be determined, light scattering can be determined, optical activity can be determined, photoionization also it can detect. These are the different properties of detectors which can be determined using detector. What should be determined on the basis the detectors are selected. And next is the optical detectors. Next topic is here. These include UV visible. Optical means optical instruments such as UV visible spectrophotometry are most widely used for HPLC instruments. Uh, these types here for absorbance detectors are available for fixed wavelength UV detectors, variable wavelength detecting using deuterium lamp, or scanning wavelength detectors. These are the three types of observant detectors. So as rise time of 0.1 second is needed for the fast measurement of in the HPLC. Even the 0.1 second can be detected using these optical detectors. So further, this fixed wavelength detector is there and variable wavelength detector. In fixed wavelength detector, it is used in the light source that emits maximum light intensity at one or more discrete wavelength. The wavelength of 250, 280, 313, 334, and 360 nanometers use narrow band pass to interfere these filters. So at this range, these fixed wavelength detectors are used. In variable wavelength detectors, it is usually for the wide band pass visible spectroscopy coupled to chromatographic system, such as in the complex spectrum of 190 to this can be used for 190 to 600 nanometers for variable wavelength detectors can be used. So next is the schematic diagram of the detector. The sample is passed through this, and the reference photodiode is nothing but the reference. It will give reference chromatogram with this, and further mirroring and takes place, and it is passed to the convex lens through pre-lensed lamp. So it can be determined here. So next is the infrared absorbance detectors. Infrared detector cells are similarly constructed used in the UV radiation. Here also from the volume of 1.5 to 10 microliters can be determined using means for the different quantity also it can be used for different detectors here. Quantity of the sample. So the volume of 1.5 to 10 microliters can be determined using infrared absorption detectors, and the range of 2.5 to 1.5 micrometers can be determined. So next is the fluorescent detectors. Here it is similar to design of fluorometer, where instruments are based upon the xenon source. This source of lamp will be xenon lamp, or employing a grating monochromator to isolate the fluorescence of radiation. Here we are going to use xenon lamp for the detection of the fluorescent. And next is the optimization of separation. This optimization of separation is nothing but the whole experimental part. How you are going to optimize the experiment of HPLC. This is the optimization of separation. How you are going to separate the sample using HPLC. Here, the primary aim of the separation of the compound or a complex mixture is to achieve adequate resolution with high purity in the short time. How you are going to adequate the resolution of high purity in the short time? So here first the proper HPLC system must be selected. Which HPLC are you going to use? It should be selected, and the parameter of stationary and mobile phase are selected. This optimization is nothing but the operation which is done using the system by selecting the stationary phase and the mobile phase, which one has to be selected, and by the HPLC system, which system we are going to use. Ion exchange chromatography, different chromatography decoration for different techniques. So the type of characteristics of column packing also, the porous particle size, good packing procedure, high quality packing materials also influence the column length and the particle size. This also is included. And the development of computer control. This are nothing but this done manually, and this we are going to select using the computer. The development of computer control HPLC system is enabled system automation optimization technique based on the statistical experiment. So the method here first, the column and the detects are chosen carefully. Which column has to be selected? There are different columns which have seen the tabular right in the previous, and we are going to select for the different column and the detectors which are going to be used for different sample. Depending on the sample, we are going to select the column and the detectors. And next is, this is the chromatogram. What we are getting after the illusion. So this one are, for example, if you take this, yes. Yes. This methanol, tetrahydrofuran, and water. These are the mobile phase. What we are going to use in the chromatography, so that these are the separate peaks 1, 2, 3, 4, 5, 6. These are the different compounds present in the given sample. It is separated by using detectors, and this is the chromatogram. This is known as the chromatograms, and here we can see the different peaks. We can denote for different values. We'll be having some standard procedure protocols where we'll get the value different. You can identify the peaks by seeing those values. So here one is the benzyl alcohol. This peak is the benzyl alcohol, and 2 is the phenol, and 3 is the 3-phenyl propanol, and fourth one is the 2,4 dimethyl phenol, and 5 is the benzene here, and 6 is diethyl phthalate are separated by column chromatography. So yeah, these are the methanol, tetrahydrofuran, and water are used as a mobile phase. So you can see here with the different concentration, where we have taken water with a different ratio. Water we have taken 50%, tetrahydrofuran we have taken 42.94, and methanol 7.5%. Why these are all are methanol is a polar solvent. So by varying the polar and non-polar, we can elute the sample easily. Even the sample will be polar or non-polar, right? So when it mixed with the polar, the sample elutes easily. So the methanol is a polar solvent, and tetrahydrofuran, what we are going used here as a mobile phase, is a moderate polar, and water is also a polar solvent. A tetrahydrofuran, it is lightly it is lightly moderate polar. It is not polar. So by varying the concentration of this ratio, see, you can see here, it will be separated. If you see the difference between this chromatogram and this, by varying the ratio of this mobile phase, we can separate it easily. You can see the separation. So this can be this this these two with the reference with the standard internal standards, means already determined compounds. We can see these chromatograms by varying this. See here, methanol we have used 31.8%. So you can see the difference between 1 and 3 compound. There is a uh, more distance, so it can be separated easily. So here methanol we have taken 0%. Here it was 31.8%. When methanol is 0, it is separated here. By varying the concentration of the mobile phase, we can be separated. And these all 5 chromatograms are for same sample. This is not for different sample. This is the same sample what we have taken. Uh, this 1, 2, 3, 4, 5 are here. See, benzyl alcohol, 2 is the phenyl, 3 is the phenyl propanol, and 4 is the 2,4 dimethyl phenol, and 5 is the benzene. Here also this 5 is benzene itself. It's not other thing. So this, by varying the different ratio, we can be separated easily, polar and non-polar. And these are the separated products. It can be seen clearly. So in general, mobile phase with no polarity are used with a polar bond phase. So if the mobile phase is not having the polarity, it can be used for polar bonded phases, which is stationary phase. For non-polar bonded phases, the mobile phase are selected from solvent which is having high polarity. So non-polar bonded phases ke will be selecting the mobile phase with high polarity. This is the conclusion of, and this is for the different solvent, methyl, octyl, and octadiol with the time. This is not much important. And next is Yes, here comparison of chromatogram for 9 compounds. For we can almost the sample will be containing whether it is having 9 or 10 compounds in the sample. It can be separated. Seen here with for different 9 compounds of polarity obtained of the ratio here what the methanol and water is used in the ratio of 50-50%. So here only two mobile phases are used, which are methanol and water, which is in the ratio of 50% each. So if you take 100 ml of methanol, even the water is in the 100 ml, both are 50% can be used to elute this sample. So 9 different compounds are present, such as one is the phenol, two is the benzaldehyde, three is the acetophenol, nitrobenzene, methyl benzoate, and methyl oxalate, and fluorobenzene. 8 is the benzene, and 9 is the toluene. So these are separated with the time. You can see here. And next is the advantages of HPLC. What are the advantages? It can be separated very fast within a minute. Useful for the separation method for high resolving power. Quantitative method can also be analyzed and is especially used for resolving optical activity compounds through types of column. Chiral stationary isomers can be identified, and the technique is applicable to small amount of the samples where traces of amount solute may be determined. For small amounts also it can be determined, and further it's applicable for pharmaceutical and food processing industries. These are the advantages. Lots of advantages are there. Go through this. This is the end of the unit 15. And that is HPLC, high performance liquid chromatography. In the next class, next week I will be taking this, the last topic, ion exchange chromatography. I will be taking in the next class, by next week itself. If there is any doubt, kindly ask, or I will end the